All right, so we've been working a lot with squares and square roots in our Pythagorean theorem problems. So a logical next step is to talk about radical equations. So in this case, it says a radical equation is an equation that contains a radical expression with a variable in the radicand. So radicand is just our symbol here, and that just means there's a variable in there somewhere underneath. To solve a radical equation, first isolate the radical and then use exponents to remove the radical. So let's go ahead and move on to some examples. So here I have the square root of x plus 5 equals 13. So what I'm going to do is subtract 5 from both sides, which will give me the square root of x here on the left equals 8. And then to get rid of a square root, we're going to do the opposite and square both sides. So this will give us x equals 64. And that's our answer. So let's do another. On this one, since 3 is positive, I'm actually going to subtract 3 from both sides. So I have negative square root of x equals negative 3. And then to get rid of this negative, I'm going to divide by negative 1 on both sides. So I'm isolating that square root. Negative 3 divided by negative 1 is a positive 3. And then my last step to get rid of this square root is to square both sides. So x equals 9 in this case. So here's a more complex one. Let's try this one first. So the very first thing we would do is we would move this 3 because we're trying to isolate our square root here. We're trying to get this part all by itself. So I'm going to start by subtracting 3 from both sides. Which will give us 16. Then I'm going to divide by 4 on both sides to get rid of this 4, which is 4. Now at this point, since my radical is isolated, I can square both sides, which will leave me with x plus 2 equals 16. And then the very last step to finish this out is to subtract 2 from both sides. So we get x equals 14. All right, sometimes you'll have radical expressions on both sides. Now, since they are both isolated nicely for us, we are simply going to square both sides. Which gets rid of those radicals. Now I just have a problem where I have variables on both sides. So I'm going to continue this by subtracting 1x from both sides. So that'll give me x minus 1 equals 4. And then I'm going to add 1 to both sides. X equals 5 is our final answer here. All right, extraneous solutions. So what is a little bit challenging about these problems is that sometimes you can solve it and do all the steps entirely correct, but then it's still not actually a solution. So after we find our solutions, we actually need to check every single one of them. So I'm not going to go back and make us check these because beforehand I already knew they worked. So I'm not going to make us check all of these, but really anytime you do one of these problems, you want to check your answer to make sure it's not what we call extraneous or extra. So I'm going to start on this one by subtracting 10 from both sides, which will give me negative 9 equals the square root of 3x. At this point, I do need to square both sides. And you have to be careful because if you type this into your calculator, it'll tell you it's negative 81. So if you're using a calculator, you're going to want to put some parentheses around your negative 9. But negative 9 times negative 9 is positive 81. And then you have 3x. So from here, we will divide by 3 on both sides, which should give us 27. So this might be our solution, but we have to check. So I'm going to plug it back in. And here, 3 times 27 is 81. And then the square root of 81 is 9. 9 plus 10 is 19 though. These are not equal. So that means that this was extraneous and there's actually no solution. Okay. Sometimes you might have multiple answers and only one is extraneous, meaning you would have one solution instead of two. But if you only have one solution and you plug it back in and it doesn't work, then there's no possible solutions. So that's an example of one of those. Let's do this other one on the right here. So the first thing I'm going to do is subtract 13 from both sides, which gives us the square root of 5n equals negative 10. And then to get rid of that radical, I'm going to square both sides, which gives us 5n equals 100. And then I'm going to divide by 5 on both sides. And we end up with n equals 20. But I have to check and make sure that works. So I'm going to plug it back into my original problem. So instead of n, I'm going to plug in a 20. 5 times 20 is 100. And then 13 plus 10 is 23. So we end up with 23 does not equal 3, which means that's not a solution. And since I don't have any others to test, I know I have no solution. All right. So let's do a couple more examples dealing with our extraneous solutions. So here it says determine which solution, if any, is extraneous. So they gave you the two solutions that they found when they worked out the problem. And we're just going to test them. So we don't have to solve the whole problem. We just have to test the ones they gave us. So I'm going to start by plugging in 5. So 6 times 5 minus 5. We want to know if that square root is equal to 5. So this would be 30 minus 5 gives us 25. Root 25 is 5. So this first one worked. X equals 5 worked. So let's check out 1 here. So 6 times 1 minus 5 is that 1. So 6 minus 5 is 1. Square root of 1 is 1. So they actually both work. So we're going to say no extraneous solutions. So they found two solutions and they both are correct. So there are two solutions to this problem. Moving downwards, I'm going to plug in negative 1 first. So I'm going to have 12 times negative 1 plus 16. We want to know if that's negative 2 times negative 1. So this would be negative 12 plus 16 is root 4. We want to know if that's equal to a positive 2. And here we get 2 equals 2. So that works. So now we have to check 4. So 12 times 4 plus 16, we want to know if that root is equal to negative 2 times 4. So here we'd have 48 plus 16, I believe is 64. So we have root 64. We want to know if that's equal to negative 8. And root 64 is 8. That does not equal negative 8. So we would actually say that this one does not work. So P equals 4 is extraneous. All right, we're going to do one more example in our notes, which is a word problem. So this one says the period of a pendulum. So first of all, a pendulum is anything that's swinging back and forth. So we have an example here. This is a pendulum swing where it's almost like a marble swinging back and forth. Period is the length of time. So the period, which would be measured in seconds, of a pendulum is given by the function P equals 2 pi times root L over 32, where L is the pendulum length. And that's going to be measured in feet for us. A pendulum has a period of 4 seconds. Is this twice as long as a pendulum with a period of 2 seconds? So let's do a section for 4 and a section for 2, and then we can compare. So P stands for period. So that's where I'm going to put in my 4. And then what I'm going to do is I'm going to divide by 2 pi to isolate that radical. And I'm going to go ahead and use approximate form instead of exact form because it's going to get kind of crazy with that pi under there. So this is going to be 0.64 if I round to 2 decimal places. And now to get rid of that radical, I'm going to square on both sides. So that's going to give us 0.41. And then last thing I need to do is multiply by 32 on both sides. So if I'm still rounding to 2 decimal places, that leaves me with 12.97. And this was in feet. So this is saying that this length of our string or whatever they're using is basically 13 feet. So now we're going to do the same thing, but we're going to use 2 for P for 2 seconds. So we will start by dividing by 2 pi. Which to 2 decimal places would get us to 0.32. And then I'm going to go ahead and square both sides, which gets me to 0.10. And then we'll multiply by 32 on both sides. So that ends up with me getting 3.24 feet for the length. So it wants to know if, since we doubled the time, if we're also doubling the length, but we're not. We're actually about roughly, like if we were talking about going from 3 to 12, we're roughly about 4 times bigger instead of twice as big. And really that is because when I take this period and I make it twice as big, let me make some space here. When I take this period and I'm going from 2 to a 4, I'm doubling it. And at a certain point, I'm going to have to square that to get rid of the radical. So it's going to end up around roughly 4 times as big. Whereas if I had, let's say I had 2 and 6, which means I'm tripling it, my final rope length is going to be 9 times as big. So that's where that's coming from. All right, so that's the end of our notes for today. You do have a Delta Math assignment you are working on.